All right, this is where we were in the last video. So this is Caloris Basin. Um, and interesting enough, on the opposite side of the planet, Mercury, um, so exactly, opposite this giant impact, we find this. And they call it, I've seen it referred to as weird terrain. This is called chaotic terrain. It's just this odd looking um, feature, which can is basically explained by this huge collision, um, something that was planet size that collided with the early Mercury, roughly almost 4 billion years ago, 3.8 billion years ago, and the collision was so great it almost um, broke Mercury apart. In fact, nowadays, what we do, of course, is computer simulations to check and see, what was the size of the impactor that would have caused this kind of thing, and how close did it come to breaking Mercury apart. All right, so yeah. So that's this was. See, it's still speculated that this weird terrain or chaotic terrain on the opposite. I mean, it's not a coincidence that it's on the opposite side of Caloris Basin. So, people have speculated that this was caused by that impact. Of course, that in and of itself is not proof. We have to investigate even more. Um, and I don't know if we're going to be able to do that from just, um, you know, uh, basically pictures of Mercury. We might actually have to someday land on Mercury, although there's nothing like that planned. Um, yeah. All right. So here's this is kind of a flattened out map of Mercury. You can notice that the difference in elevation goes from about 8 kilometers below, if you want to call it surface level, where the surface level would be, zero, and then there are some mountainous regions that rise about 8 kilometers above. So this is very similar to the moon, right? Um, there's Caloris Basin right there. There's the chaotic terrain. Remember, this would be a complete circle, of course, where we just flattened out. Notice some of the features some of them are named after classical composers. Mozart. Where's another one? Rachmaninoff is a famous classical composer. Beethoven, and then there's some that are famous artists. Raphael, Rembrandt, and so forth. All right. So anyhow, that's just these are different names that we for features on Mercury. All right. So So now Mercury is kind of a very odd place, because it doesn't have an atmosphere. It gets really really hot when the sun is facing Mercury on the sunny side of Mercury, and then on the opposite side, when it's nighttime. So look at the difference in temperature, and we can talk about it in terms of Fahrenheit. So 820 degrees Fahrenheit, when the sun is facing on that side of Mercury, the daytime side, and then it drops to negative 320 degrees Fahrenheit on the nighttime side. That's again, the reason for these extremes is because there's no atmosphere. There's no atmosphere whatsoever to just hold on to that heat. Um, and the fact that Mercury is so close to the sun. So just to give you a sense of this temperature, it's as though if you had your oven on broil, right? So you turned it up as high as it possibly can. This is about twice that temperature. All right. Now, has been detected some trace amounts of gas. And let me explain what's going on here. Okay, so again, Mercury does not have an atmosphere. Okay, um, let's say, for example, a comet hits. A comet would be a good example. It doesn't even have to be a comet, um, but something that has some kind of gaseous material that hits Mercury, collides with it, causes one of these many craters, um, and so what happens to that gas? So over the course of time, we just talked about the fact that the daytime temperature is 820 degrees Fahrenheit or 710 Kelvin. What's going to happen is any gas molecules that are near Mercury would be subjected to that high temperature. In other words, they receive what's called thermal energy, heat, basically, and so those gas molecules will easily, especially with with this temperature, 710 Kelvin, they'll easily reach escape velocity. So even if Mercury temporarily has just some gas molecules, and it's just a tiny amount. Okay, I want everyone to understand that it's not like there's a huge atmosphere or something like that. It's fleeting, right? It's going to leave over the course of time, because those gas molecules will easily reach um, the escape velocity once they get heated up. Now, when they get heated up, they're traveling in all sorts of directions, so they're not necessarily leaving the surface of the planet. But let's say with random motion, some of those gas molecules will go in a direction away from the planet, and since they're traveling faster than the escape velocity, they will go off into space. All right, so. All right, so that is basically Mercury's non-existent atmosphere and what happens to any gases that do encounter Mercury. There are actually ice, which this was actually a big surprise. One of the big surprises from the Messenger mission when we went over the poles of Mercury, there were some craters that never ever are directly exposed to the sun because they're in the North and South Pole. And Mercury is not tilted the way our Earth is tilted. It's almost directly up and down, north and south, but face perpendicular to the sun. So these don't ever get sunlight, and so there's actually frozen ice in the shadows of these large craters. So that was, again, that was a big surprise. This is just showing you this where this ice is in. This is called false color. We do this often in astronomy to indicate where the to distinguish one feature from another. Right here, this is Mercury's interior. So of course it has it has a thin crust. It has a mantle, and it has a surprisingly large core made of iron and nickel. Why do we know that it's made of iron and nickel? Well, we did that example to find the density of Mercury, which turns out to be a little smaller than the density of Earth, and yet Mercury is much smaller. It's only about a third the size of the Earth. So how could its density be so great? Well, the only way for that to happen. Oh, by the way, the density is about 5.4. For the Earth, it's 5.5, and it's of course grams per cubic centimeter. The only way for that to happen for Mercury is to have a really large core of iron and nickel. Let's see. Let's see. What is this all about? The crust and mantle. Mercury's high average density suggests its interior is iron-rich, with only a thin. Okay, it's two possible reasons for the thin crust. Silicates don't condense as easily as iron in the interior. In the inner solar system where Mercury was formed, and also the rocky crust was blasted off by an enormous impact. Well, we just talked about an enormous impact, that Caloris Basin, right? So that's why we think. Well, it's probably a combination of these two reasons. So yeah, it probably is, like I just said, it's a combination of these two. Um, so you don't have as much silicate condensing in the area right around where Mercury is from the sun, the distance that Mercury is from the sun, and that huge impact that is the remnants of which is what we call Caloris Basin. This is just an example of this large impact hypothesis. So some object comes in, roughly maybe a little bit smaller than Mercury. It hits, and if let's say there was a large rocky mantle initially, which we don't know. If there was, after this collision, a lot of that rocky mantle got shot off, and then what remained is a little bit of rocky material, and then mostly an iron core, which accounts for its high density. Right? Now, Mercury actually, the fact that it does have an iron-rich core, it actually does have an overall magnetic field. It's not a very strong magnetic field. Okay, so this was detected by the Mercury spacecraft. I'm sorry, the Magellan spacecraft. Geez, I'm not even. That's the wrong spacecraft. Magellan was for Venus. Sorry about that. The Messenger spacecraft. Yeah. So there's so many spacecraft. Sometimes it's hard to keep track. But it's the Messenger spacecraft that orbited Mercury for a long time. There is another spacecraft that in the year 2025, if you're watching this and it's already past that, there's another spacecraft that's in orbit around Mercury. All right, and so this is the mission right here. It's called Bepi Colombo. Bepi Colombo will arrive if you're watching this and it's already 2025, then it's already gotten there. Hopefully, it got there safely and is in orbit around Mercury. This is a combination of the European Space Agency, which is called ESA, and then the Japanese Space Agency as well. So these two entities were going to send a spacecraft separately, but then they basically combined. The part of it is the Japanese spacecraft and part of it is the European spacecraft. All right, so that's Bepi Colombo. All right, here, let's get back. Again, that's a future mission to kind of, investigate further some of the findings that the Messenger mission gave us. What else? Okay, so all right, now this is an interesting thing. Actually, before I go on, let's talk a little bit about our moon, right? So our moon goes around the Earth. Well, this is not the moon, but it goes around the Earth, and it has what we would call a 1-to-1 resonance. That is, the time it takes the moon to rotate around on its axis once is the same time that it takes to go all the way around the Earth. For Mercury going around the sun, Mercury goes around the sun twice, and every 2 times it goes around the sun, it spins around on its axis 3 times. and that's called a 3-2 resonance.